So, in the last lecture we introduced the concept of a reciprocal lattice, where if you have a crystal, then from that crystal you can generate a Bravais lattice using your real space translation vector R, which is written as linear combinations of A1, A2 and A3. This is a real space translation vector. So, from your crystal you can generate your Bravais lattice in real space. You can also generate for the same crystal another set of points which is in another space, not in real space, but in another space which is called as a reciprocal space, where distances are measured in inverse of length. So, it is another space which is called as a reciprocal space, and in that space you can generate a set of points which correspond to the same crystal, but you are drawing it in another space which is called as a reciprocal space using these fundamental vectors g1, g2 and g3 in the reciprocal space. And you can generate a set of points corresponding to the crystal using linear combinations of g1, g2, g3, where these are integers h, k and l, and g1, g2, g3 are the fundamental translation vectors in the reciprocal space, and the two translation vectors are related by g dot r bar is equal to 2 pi. One is in the real space, one is in the reciprocal space. And from here you can also link your fundamental translation vectors in the two spaces by gi dot aj is equal to 2 pi delta ij. And this gave us a way to calculate g1, g2, g3, and therefore help us to draw the equivalent reciprocal lattice, where g1, g2, g3 are related to a1, a2, a3 by these forms, which satisfy, all of these forms satisfy this expression. And so, each crystal has a real space lattice in real space a1, a2, a3. You can also construct a reciprocal space lattice. So, let us try and do one example where I can take first a body centered in real space. Let us take a body centered cubic lattice. So, in real space, if you have a body centered cubic lattice, you have points which are at the edges of a cube, but there is one point which is sitting in the center of this lattice. Okay. And let us define my coordinate axis. So, my coordinate axis, this is my, let us take this as my z axis, this as my x axis and this as my y axis. And you would recall that in some of my earlier lectures I have already drawn the fundamental, one way to choose the fundamental translational vectors in real space a1, a2, a3 for the body centered lattice as these points. One is of course this is your origin. The second point is a body centered point which is sitting for a lattice which is in the xz plane, I mean the face of the square or the cube is on the xz plane, and the body centered point is sitting along this axis. So, this is a point which is sitting in the x minus y direction and plus z direction, and the third point is sitting. So, you have a point which is going this way, and there is another point which is sitting here. So, this is in the minus z direction, this is in the minus z direction, minus y direction. Of course, this is your minus x direction, one point here, one point in the minus y, plus x and plus z direction. This point is in the minus z plus x plus y direction. So, this is your third vector A3. A1, A2, A3. These are actually your primitive vectors for your body centered cubic lattice, and you can write these vectors A1, A2, A3 as A1 as, if the cube has sides of length A, then A1 is A by 2, this point is minus x cap plus y cap plus z cap, because this point is along the minus x cap direction plus y plus z. A2 is equivalently plus x cap minus y cap plus z cap direction. A3 is A by 2 x cap plus y cap minus z cap direction, A3. So, these are your fundamental translation vectors for a body centered cubic lattice. So, using A1, A2 and A3, we can write down our vectors in reciprocal space. The fundamental vectors in reciprocal space, G1, which is pi by A, y cap plus z cap, G2 which is pi by A, x cap plus z cap, and G3 which is pi by A, x cap plus y cap. And now we can actually sketch what is this type of a lattice that you can generate with G1, G2 and G3. So, this was your body centered lattice. We had a BCC lattice in real space, and from the BCC lattice we are now generating another lattice corresponding to the BCC lattice in reciprocal space. What is that lattice? Let us find out. So, if you have a cubic lattice with lattice spacings A or lattice constants A, we know that it transforms in reciprocal space to these with lattice spacings 2 pi by A. Now, this is your BCC lattice which we had drawn earlier in real space. This is in real space and this is reciprocal space. These had lattice constants A. So, this cube will go into a this cubic structure will actually go into a cubic structure with size 2 pi by A. These were your BCC points which defined your primitive lattice vectors A1, A2, A3, and from there we got G1, G2, G3 which are half of 2 pi by A, y cap cross z cap. So, this gives a point in the yz plane. This gives a point which is halfway on the x axis, halfway on the y axis, and this gives a point on this face, this gives a point on this face. So, what do you have here? You have a face centered cubic structure. So, the BCC lattice in real space goes over into an FCC lattice in reciprocal space. So, corresponding to a crystal which can have a BCC lattice in real space, you can also geometrically construct the reciprocal lattice corresponding to that lattice, and that turns out to be, for a BCC structure, it is FCC, and similarly you can find out for other lattices also. So, with this concept of reciprocal lattice, let us see where is it useful. So, let us look at what is the use of this reciprocal lattice that we construct. And here let us recall our discussions of X-ray diffraction, where we had considered the following. You have a source Q which is very far away and you have a crystal, and we looked at the plane waves which were reaching this crystal with a wave vector k, which were reaching this point P on the crystal. This is of course r plus r, where this is the position of the point in the crystal. So, this is our crystal, and then the X-ray from here starts diffracting. So, each point out here becomes a secondary source and it starts diffracting light from this point. So, you start getting secondary wave, spherical wave fronts, and as a result you get a diffracted beam or a scattered beam. At another point B r prime, and this is where you are measuring the scattered beam, and this is of course r prime minus r, and you are getting the wave fronts reaching point B. And we had found that if I write the intensity at point B using the electric fields that are hitting point P and then diffracting out and integrating over the entire crystal, then it was proportional to the square of the initial amplitude of the wave which is coming divided by inverse square of the distance of B from the crystal. The intensity dies down as square of the distance from the crystal, you naturally expect it. And there was another term which was the Fourier transform of the density of points in the crystal. That was rho of r e raised to minus I k dot r d cube r the whole square, where this scattering vector k was equal to k prime minus k, where k prime is the wave vector of the scattered wave. So, this is the wave vector of the scattered wave, and your scattering vector is written as k prime minus k. This is your incident wave vector and this is my scattered wave vector. Now, let us look at this intensity, and you know that rho of r you can now Fourier expand in your reciprocal space, and so you can do an expansion of this density in also reciprocal space rho of g. Because of periodicity of the lattice and translational invariance, we saw that rho of r can be expanded in the reciprocal space, and you can write it as e raised to I g bar dot r bar, where e raised to I g bar dot capital R becomes equal to 1. So, translational invariance allows you to write this in terms of this, and your reciprocal lattice vectors satisfy this condition. So, this we can put it back in the intensity, and you can get your intensity at point B. The scattered intensity at point B is A naught square by r prime the whole square, summation over the reciprocal lattice vectors, integral over the volume of the crystal, rho g e raised to I g minus k dot r bar d cube r the whole square, or IB is proportional to A naught square by r prime the whole square, summation over all the reciprocal lattice vectors in your reciprocal lattice, rho of g, integral over the volume of the crystal e raised to I g minus k dot r bar d cube r. So, now we have introduced our reciprocal lattice vector. For a given lattice, we construct the reciprocal lattice, and that is associated with reciprocal lattice vectors, and now in our scattered intensity this reciprocal lattice is appearing explicitly. How does it help? If I write down my scattering vector, this is my scattering vector k, and g is my reciprocal lattice translation vector and my scattered intensity depends on this integral, the value of this integral e raised to I g minus k dot r bar dq bar. We have seen that my scattered intensity at point B is dependent on this value. If you look at this integral for g equal to k, namely for reciprocal lattice translation vectors which are equal to the scattering vector g equal to k, the above integral e raised to I g minus k dot r bar dq bar becomes equal to V, because this will become equal to 1 if you integrate over the volume of the crystal. This will be related to the volume, and for g not equal to k, this integral V is e raised to I g minus k dot r bar dq bar. Now, these factors are just sines and cosines, and if you integrate it over this entire large volume of the crystal, this will average out to 0, because these are just sines and cosines which are spread over a distance r with these wave vectors. So, if you integrate it over a reasonably large crystal, this integral will be equal to 0 if g is not equal to k, and it will be equal to 1, or it will be, this integral will equal to the volume of the crystal if it is equal to k. So, this scattered intensity, which is written as a naught square by r prime square summation over all lattice vectors rho g integral of e raised to I g minus k dot r bar dq bar the whole square over the volume. This integral e raised to I g minus k dot r bar dq bar can be written as delta of g minus k into the volume, where this is equal to 1 if g is equal to k or k is equal to g, and is equal to 0 for k not equal to k. This is equal to 1 if k is equal to g, and it is not equal to, and it is equal to 0 for k not equal to g. So, your intensity at point B becomes proportional to a naught square by r prime square rho g square. So, my intensity at a given point in the lattice becomes maximum if my scattered wave vector becomes equal to g, then I get a finite intensity, IB is not equal to 0. If k is not equal to g, if my scattering vector k is not equal to g, my IB becomes equal to 0. I get no scattered intensity, and this is the condition for diffraction. The condition for diffraction of X-rays from a crystal, namely under what conditions IB, the intensity at any scattered point is not equal to 0. The intensity at a scattered point at any other point, the scattered intensity at any point is not equal to 0 if my scattering wave vector is equal to my reciprocal lattice vector. And this condition of diffraction is called as the Laue condition of X-ray diffraction. This scattering vector is the difference between the scattered wave vector minus the incident wave vector. if the scattering vector is equal to the reciprocal lattice vector, only then my scattered intensity is not equal to 0. Namely, I will get a finite bright point at that location, and intensity at that point will be equal to 0 if the scattered vector is not equal to this. Namely, I will get no intensity, or the average intensity at a point B will turn out to be 0 if the scattering vector is not equal to your reciprocal lattice vector, and we will see the interpretation of this in the next lecture.